Honeybee queens mate with a large number of males. I mean, estimates vary depending on the population from 6 to more than 20. And that raises two important questions. Why? And what are the consequences? And those are different questions. And I deal with them differently in different modules. The evolution of polyandry is the why question. Why do they mate with so many males? And that's what I'm going to be addressing here. So the queen flies through the air, and she encounters large numbers of males in drone congregating areas. And she flies through and she mates with sometimes 20 or more in rapid succession. She collects their sperm. She stores it away in her spermatheca to last her egg-laying life. So many people have asked the question, why do they mate so many times? And why do they go to all the trouble to mix it up so well, as I've discussed in previous modules? There are four main hypotheses that people take seriously and think about. The first one is, well, they need the sperm. One male just doesn't simply supply enough, so they have to mate with more males. The second is that it provides a more effective division of labor. If you mate with more males, you have more genetic variation. If you have more genetic variation, then it gives you a better division of labor because things get done better and things are covered better and you're less likely to fail. The other is it provides resistance to diseases. That if you have more genotypes, more genetic variability in the colony, then you're not likely to have a disease come in and wipe you out, that you're going to be more resistant. And then the fourth one is that they are hedging their bets against homozygous sex alleles. So to address the first question, or first hypothesis that, the males just can't make enough sperm to fill a queen up. Well, that's really kind of hard to believe. The males are huge. They're large in size. They're the size of a queen. They're double the size of a worker. And if you look below here, we have the male's genitalia. They're massive. And all that is contained inside of the abdomen. And this part right here, that's the sperm they produce right there. All this other stuff in here is mucus and things they put in as a plug to plug the queen up. And this is a male genitalia here being inserted into the sting chamber of a queen. So they have huge, there's no reason why, I mean, it's hard to expect or explain why a large apparatus like that couldn't have made more spermatozoa. So it's unlikely that they're limited by the amount of sperm that they can deliver. Also, here's a figure that shows a relationship. You've got males in the bottom. This is the number of sperm they produce. And here you have females. This is the number of sperm that they maintain in their spermatheca. And the line you see through here is the relationship with many different species of ants, bees, and wasps. And as you can see throughout, there is an overall trend that when the females need more sperm to fill their spermatheca, the males are able to produce it. Again, an argument against this, well, they need to mate with more males because they need to get more sperm, and individual males can't produce enough sperm. It's more likely that there's another adaptive explanation. Also, when you look at the ant species, Solenopsis invicta, a queen saves in her spermatheca about 5 to 7 million sperm, about the same as a honeybee queen. The males produce about 5 to 7 million sperm each, and she mates one time. So there's no problem with her getting enough sperm from one male, and the males are much, much, much smaller than she is, but they get sufficient. And the stingless bee, Melipona quadrifasciata, she receives about 1.5 million sperm and stores it in her spermatheca. Males produce about 1.5 million sperm, 1.52 million sperm. That's what they deliver to her. So she takes it all, and she mates one time. So there's no problem with her getting in one mating all that she needs. And they're both of these species are very social, like the honeybee. So the queen takes in about 100 million spermatozoa from all of her different male mates that she mates with. So she mates with about 20 males. They each give her about 5 million. She takes in about 100 million, and they come in through here. The male deposits it all the way back here into the lateral oviducts. Then the sperm are pushed back through this way, and as they're close to the spermathecal duct, they migrate up into the spermatheca. So there's a machinery here that she has that results in the acquisition of sperm from many different males, and all of them to be represented in the spermatheca. With this kind of machinery, the sperm of any one male cannot dominate the content of the spermatheca. She controls it. She controls it so that the sperm that get into the spermatheca are representatives of most or all of the males with which she mated. So that's the first hypothesis, that they need to mate with more males because no one male can give them enough sperm. I believe that that's falsified. The next one is that it makes them somewhat resistant to diseases, pathogens. Honeybees have a plethora of pathogens. There's viruses that attack the larvae and the adults. Bacteria attack the larvae. Fungi attack the larvae. And there are protozoa that invade the intestinal tracts of workers and cause dysentery. You can see here they've defecated on the outside of the nest. Think of the problem. It's an epidemiologist's nightmare with respect to diseases and disease spread inside of a nest. The overall, at any time, there's about 7,000 larvae. And here we have children and babies in a nursery, right? So think about if those babies in the nursery, if there were 7,000 of them, and there were 8,000 nurses that were taking care of them, and altogether they were making 1,000 visits a day to them and feeding them 100 times. I mean, look at the tremendous potential for exposure to disease and disease pathogens. It's daunting. Genetic variation slows the spread of disease. That's the hypothesis. And we can examine that in a model. So let's assume that these cells represent cells that contain larvae. And let's assume that this queen mated one time with one male. Let's just assume, for simplicity, that all of the larvae have the same genotype. They're all A genotypes. They're all the same. So we have a virus, some virus variant for some kind of a disease, gets introduced into one of the cells, this cell here. And this virus is of some genotype X. And let's assume that X is really not very well designed to infect A. So when X is in contact with an A-type larva, once it gets into it, it reproduces kind of slowly. It doesn't do real well, but all the time it's replicating. So, I mean, they're going through very, 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 very rapid generations inside of this larva with this A-type of genotype. And in time, a mutation occurs. And then this mutation perhaps somehow gets introduced into the next cell, this cell. And, it's a little bit more similar or a little bit more capable of manipulating this A genotype than the X was. And so then it sickens it a bit. It replicates more than it did in the A type, but then it spreads again. And this time it mutates into an A form. And that then spreads into this cell here, which has an A-type genotype. In other words, the genotype of the virus is well suited to the genotype of this particular larva. And what it does then is it replicates really fast, and it kills the larva, and it spreads very rapidly throughout the whole nest. And so then you have a sweep of the A genotype, and all the larvae are sick or die. So this is what can happen when you have limited genetic variability. Let's assume you have another colony where the queen mated with a lot of males, and you have a lot of genetic variation. So if you look at the genotypes of the larvae in these cells, there's E, D, C, B, F, the whole variety. So now the X virus variant invades the A type larva. It then weakens it somewhat, but it's not a good match at all inside this environment. So just it weakens it some, but produces some additional virus particles and some mutations. So let's say a mutation K that came from here, and it got into this this cell that has genotype F, and it's a little bit more adapted to this genotype. So you can see it's darker. It did a little more damage to it. It replicated more and faster, but then it produces another variant, an E variant, say, comes out of it, and the E variant invades an E cell here, kills the larva, and produces a whole lot of viral particles. And then it also goes into the A cell next to it, or the cell next to it that has an A larval variant in it. And there it produces a D that goes to the next one, where it's close to a D. So it's more virulent to it. It weakens it more, and it produces more viral particles. But it also may have produced a D variant that invaded a cell with a D type in it. But you see the picture here. You're not getting this sweep of all of a sudden everybody's wiped out by the virus, because every time a virus moves into the cell next to it, there's a high probability that even the mutation that it produces, when it gets into that cell next to it, it's going to be encountering a genotype of the worker that's different from what it became adapted to in the cell that it was in, etc. There is evidence for the explanation of polyandry evolving because it confers resistance to diseases. This is a study that was done by Tom Seeley and Dave Tarpey. They instrumentally inseminated queen honeybees. Some of them received just a single drone, so a single mating, and others received multiple drone inseminations. And then they followed them through the season, and they measured a whole bunch of different things on them to see what the effect was. And this is just showing one of the effects that I think is an important effect. The figures here show the average and the distribution of brood area found in these colonies after a certain amount of time during the brood rearing season. The multiple drone inseminations, the average amount of brood was higher than it was in the single drone inseminations. And they also measured the amount of disease, the disease load in these colonies, and found it was correlated with the amount of brood that was produced. So you can see here that there is evidence that the colonies that were made, where the queens were mated with multiple drones by instrumental insemination, overall did better than the ones that were inseminated with a single drone. Next, you need to review the sex determination module. I'm not going to cover that part of it here, but I'm going to cover some of the consequences. The last hypothesis that I'm going to talk about is the hypothesis that queens that mate with more males are hedging her bets against getting a bad mating, which by chance might be with a male that has a sex allele that matches one of hers, whereby she'll lose half of the brood that she produces and the colony will fail. So let's imagine that this represents the true relationship between probability of a colony surviving and the viability of the brood that's produced. This basically says that if you're losing half your brood, which you can do if you mate with only one male and he has a sex allele that matches yours, one of your two, you'll have half of your brood will be in viable diploid males. And this is saying that basically there's zero chance to survive. That you won't survive because you need to have some critical number or percentage of your brood to be viable before you can survive. So then, if you look at the relationship with colony survival, when you get up to 75% of your brood survives, then you're going to be somewhere in the middle of this curve, and then it changes shape. So down at this end here, what's happening is with each increase in brood viability, you're getting a fairly large jump in colony survival probability. When you get out here where you have a lot of high survivability of the brood, you're getting, for each increment increase in brood viability that you get, you're getting less of an increase in colony survival. So, for instance, it might make a big difference down here if you have a colony of only 2,000 bees versus a colony here that has 20,000. This one's going to have a much higher survivability than this one here. But when you get up here, if you have 20,000 or 30,000, it probably doesn't make nearly as much difference as it does down here at this end between 2,000 and say, 5,000. So this is just showing that there's a non-linear relationship between the probability that a colony will survive and the average brood viability in the colony that's due to the production of diploid males, which are a consequence of homozygosity at the sex locus. Now let's superimpose on top of that the consequences of mating with one male. So if you mate with one male, there's two chances. If the male has a sex allele identical to one of yours, or the male has a sex allele that's different from either one of yours. Remember, queen honeybees, being females, have to have two different sex alleles at the sex determining locus. The complementary sex determiner. They have to have two different ones. So if she goes out and mates one time, and say there are 10 sex alleles in this population, each sex allele is at equal frequency, so there's 1/10 or 10% of the population has each of those 10 sex alleles. She has two. When she goes out and mates, there's a 20% chance that the male that she mates with will have a sex allele that matches one or the other of hers. Either, one of the two, because she has to have two. So there'd be a 20% chance, probability, that she would have diploid males and would have 50% viable brood, that she would lose half of her brood. There would be an 80% chance that that male that she mated with would have a sex allele different from one of hers. And she would have 100% viable brood. So if she mates one time, she's either going to do this, be there, or she's going to be here. So she has a 20% chance of failure if she mates with one male. However, if she mates with a large number of males, there's a lot of different classes where she could possibly be. It's unlikely that she would mate with 10 males that match one of her sex alleles. So it's unlikely that she's going to have brood viability down in here. It's likely that if she mates with 10 different males, her brood viability is going to be in here somewhere. And this is the distribution of those probabilities, that she will have different brood viabilities mating with 10 males. So the whole relationship is shifted over this way, that where we had 20% here, it's now been redistributed over here. And now, if you look at the same criterion, anything with less than 75% brood viability, which is what this is, will die. Well, there's very few that are going to die. The vast majority are going to live. So she can hedge her bets. Yeah, she's not going to get 100%. She's going to get something less than 100%, but it doesn't matter that much whether you're at 100% or you're over in here from these matings. So individuals that mate with more males will be favored in that they're going to have a higher probability of succeeding and the colony's not dying. This is an experiment that was done by Dave Tarpey. He took 31 queens, and each of them she mated with 3 brothers by instrumental insemination. So each of them was mated 3 times. But the queen that these came from, there was one sex allele shared among these brothers with the inseminated queens. So you could get varying degrees of brood viability from the combination of these 3. And she could mate, all 3 of them could have had an identical allele, or one of them could have had an identical allele and 2 of them didn't. None of them might have. Anyway, there's a lot of possibilities there. He then looked at their survival of these colonies from one year to the next, surviving through the winter. And this was the result. If you look at the survive versus not survive, the only ones that did not survive were those that had been inseminated with one male. So it's evidence that, in fact, there is an advantage to mating with more than one male to hedge your bets against having too much diploid male brood produced and the loss of that brood.